Hello, everybody, and welcome to another Python Exchange event. I am your MC for the evening. My name is James Powell, and we have a lot to do tonight, and so why don't I jump right into it? Here's our agenda for the evening. I'm first going to give an opportunity to all of our host panelists to introduce themselves and to let them know how they can be a part of your story, making Python thrive in your environment. I'll ask our guest panelists to introduce themselves as well, and they have some prepared remarks. Then we're going to do something brand new. We're going to bring a little bit of additional hands-on technical content to this call, and we're going to ask each and every one of our panelists to take a look at a sample of scientist-style code and to give some feedback on how scientists can take this very daunting task of developing expertise in programming and actually incorporate feedback into their work to make their code better. After that, we will invite our guest panelists to share with us a couple of prepared remarks and then open up our discussion. I know our guest panelists have a number of open questions they would like to have addressed. And so with that said, why don't we start off with our introductions? For introductions, why don't we go in this order? I'd ask our colleagues from BNL to first introduce themselves, then our colleagues from LBNL, and then our guest panelists. Dan, would you like to get started?
Sure. My name is Dan Allen. I'm at the National Synchrotron Light Source 2 at BNL, and I'm happy to chat about or answer questions about building open source communities within a facility and across facilities. I work a lot on the Blue Sky project in particular and enjoy code that makes a broad and diffuse impact on science by being a small part of many different experiments. Tom, do you want to go next?
Sorry, I had to unmute. So I'm Tom Caswell. I'm also at NSLS2. I also spend much of my time working on the Blue Sky project. In addition, I'm also the project lead for Matplotlib and a core developer for H5Py. I'm happy to answer any questions or talk about how you scale projects up to have both many users and many contributors, and how to manage broad-based tools for use in science. Andy?
Yeah, thank you. I'm also from NSLS2, but my experience is more on the Beamline scientist side. I'm not primarily a developer supporting a project. I'm really interested in looking at very different libraries and using them all together to collect data and understand science and the results. And I contribute a small amount. I write a lot of code, but it's different kind of code. Yeah.
And Tanny, could you introduce yourself?
Yes, of course. Hello, everyone. My name is Tanny Chavez, and I am a postdoc at Lawrence Berkeley National Laboratory. My expertise is based on machine learning and data signal processing, so I'll be happy to take any questions regarding the use of Python for these subjects. And I'm just looking forward to the discussion today.
Cameron, would you like to introduce yourself?
Certainly would. Thank you, James. Hello, everyone. My name is Cameron Riddell. I work with James at Don't Use This Code, and I actually have a history a little bit in academia. I studied social sciences, specifically human memory, and so I am very much looking forward to today's discussion and how we can intermesh some academics with some more programming.
And now our guest panelists, Wolfgang and the other folks in New York, would you like to introduce yourselves and let us know what it is that you can do to be a part of everybody's success story with Python in their work? Wolfgang?
Hi, my name is Wolfgang Kerzendorf. I'm an assistant professor at Michigan State University for astrophysics and artificial intelligence. And I'm also the PI of the Open Science project and community TARDIS. And what I would like to talk about and questions that I can answer is, well, how to explode supernovae on your computer. And the other question that I'm really interested in is like, how do we build sustainable, inclusive, and equitable open science communities for the betterment and progress in science? And I'm here to hand over the reins to Jack.
Hi, I'm Jack O'Brien. I'm a graduate student at Michigan State University working with Wolfgang, and I'm also a member of the TARDIS collaboration. And I combine simulation and machine learning to try to connect observations and theories.
Hello, my name is Mark Williamson. I'm a PhD student at New York University. I'm also a member of the TARDIS collaboration, and I'm happy to talk about or answer questions about data visualization and making useful tools for scientists to understand their simulations.
Fantastic. And now, before we jump into our prepared remarks from our guest panelists, I'd like to start us off with something a little bit different. One of our host panelists encouraged us to include a little bit more hands-on technical content in these calls, something that could help people improve their use of some of the scientific computing tools that they may use. And the form that it's going to take tonight is, I have written just a little bit of code, no more than 25 lines of scientist-style code. Now, I don't want to use that as a pejorative because, after all, I wrote the code. So if you complain about it, I might cry a little bit. And I would like each one of our panelists to take a look at the code and then to discuss a little bit about how, if this were actual code that you were interacting from one of your colleagues, what kind of suggestions would you make to improve it in a very, very motivated fashion? So rather than just say, oh, you should write it in this particular style, try and explain, well, why does that actually benefit them in their life? In order to share that code with you, I will share my screen with you. And so behind me, you'll see my screen. And of course, I will hide in the corner here. And while our panelists review the code, some of whom are seeing this for the very first time, I'll briefly walk you through what this code is trying to do. In this scenario, we have a scientist who appears to work on some sort of detector. And they have some images they've taken on that detector. They have clearly saved some of the results of this detector into a gzipped pickle file. And it's clearly some sort of n-dimensional structure with the height, the width, the red, green, blue channel, and some time. So I guess the detector's been capturing images over time. They load in this data. They grab the left-hand side and the right-hand side. So I guess they have two detectors which are taking images at the same time. And they mean them together. Then they go through each time step and do the same thing, concatenating these for each time measurement. And then they perform a maximization. So I guess they're kind of looking at some sort of long exposure over this time axis. Then they generate a p-color mesh to visualize this using matplotlib, one for each channel, saving the result to a file. Now I can tell you, the code works. Does it work well? Well, why don't we start off with our guest panelists, anybody who wants to comment on anything, and see if we can motivate, see if we can suggest places where this code might genuinely be improved.
I mean, this is actually, I've never seen this code before, so this is very interesting. So one of the things that as an open scientist I think about is like, how can I aid myself as an as a scientist? I mean, I'm egocentrical. I always think of myself first, but I don't think of myself now, but I think of myself in 6 months, a year, 2 years, 3 years. So one of the things that I'm very, very particular about, and I'm going to criticize your code, is like file one is not a very descriptive filing. Like variables you can use to really document your code, and you can use to like think about your code, and like, it really helps not only future you, but as we're in the open science movement, all other people to sort of like, change up the variable names and understand what the code flow is. That would be my first comment.
Oh, I'll see if I can, maybe I'll make some to-dos on a piece of paper here. Does anybody else want to comment? I know there's a couple of things in here which are very explicitly things which we encourage our scientists never to do.
I guess I'll take the bait on that pickle thing, which is clearly there to annoy us in prompt response. Pickle is a really practical format because you can save nearly any Python object as pickle, but it has two problems that I think are real practical problems for a scientist. One is it's not necessarily the same across versions of Python. So if you save a file to archive it for your future self and to try to open it with a future version of Python, that may or may not work. And then the other one is that, as people who are smirking know, the unpickling process, the process of loading that data in, can run any code. And so it can be a really nefarious way for somebody to copy something out of your home directory and email it to themselves, or delete your whole home directory or something like that. So if you're handed a pickle file, you had better have a really trusting relationship with the person who gave it to you. So short-term personal use, people do it, but as a general practice, definitely discouraged.
What would you tell the scientists to do instead of using pickle if they were in that second case?
If there's a standard format that can save that data, that would be great. So if it's an image, TIFF, HDF5, even a JPEG would probably be better than a pickle. If it's a table, there are fast formats for tables like Parquet. There are universal formats like CSV. all of those things would be fine.
So I'll take the other bait James left for us, which is the import star. That's something that can be very convenient because it pulls a whole lot of things into your namespace and saves you a bit of typing. However, when you come back to read this later, in this case, it's only 25 lines of code, so you're pretty sure that any variable, you can see any variable you've defined. But if you're just pulling in all of PyPlot, that's a lot of names that now magically come from someplace and extremely hard to tell where it comes from. And if you happen to use any of those names someplace in your code, you might accidentally, start getting extremely strange errors when you call what you think is a function, but you've defined earlier, or reading the code, you think a function is defined above and just get yourself very confused.
Tom, could I also even add, similar to Wolfgang's point, if they had misspelled one of these file names here, because they're these very generic variable names, couldn't there be a confusion as to maybe it still works because it came from PyPlot, but they can't see it?
Yes. Also, the static tools for working with Python have gotten significantly better over the last couple of years. And if you're doing import star, your static analyzers fail because they can't tell where things came from.
What's a static analyzer?
A static analyzer is code that reads your code and infers what the types are. And so you can read a Python file top to bottom and say, you just use a variable you never defined. Python won't check that for you, but this extra program will walk through and highlight and say, look, you wrote file 2 without an F, without the I, someplace farther down, and highlight that before you try to run the code that there's a possible bug. But if you do import star, it doesn't know what names you pulled in, so it can't do any of that detection of using names you haven't defined. And a second suggestion I would have is this is using p-color mesh for the visualization. P-color mesh is really designed for non-evenly gridded data where you need to specify that some parts of the grid are bigger than others. Since this is a nice even image, you can use IMShow, which will be more efficient and probably closer to what was actually intended. And I guess that's in themes of, you should reach for the lowest power tool that will get the job done at any given time.
How much of a problem is it if they use p-color mesh? Obviously, scientists, they are very overwhelmed with all of the work that they have and all of the responsibilities they have. Is this a major thing or just maybe next time you go about doing this, reach for this one instead of that one?
It is I'd say it's a minor thing. The biggest there's two issues that come to mind quickly. One is this is a performance thing. IMShow is a more efficient operation because we draw the image in one shot. And second, I do not recall off the top of my head the exact behavior if you pass p-color mesh just the data array without specifying the X and Y. There are some concerns with when you're specifying the bounds of each of the quadrilaterals in the image, are you giving the values on a vertex or in the center? And depending on which one we pick as default, which I don't remember off the top of my head, we may actually drop the last row and last column because if you're interpreted as the centers, there is you have one more center than we gave you X, Y for by default. But again, I don't remember the exact behavior off the top of my head. I have to go check the docs.
I'm curious, does anybody want to comment on the use of what appears to be NumPy and these magic numbers associated with which dimension is which, and maybe suggest an alternate tool where they could name the axes and then have magic numbers?
Take a comment on the NumPy usage here, James. Mm-hmm. The first thing that jumps out to me about the NumPy is not necessarily the magic numbers, but the fact that when we do index into that array, we're specifying from 0 to H, right, which is the size of that shape there on the outermost dimension, 0 to W, 0 to C. We can use an ellipses to perform this type of indexing. Or if you want to leave it with, accession to all 4 of your dimensions, you can use explicit just colons, right? We don't need to specify start and stop if the start and stop are the first and last points.
What's a magic number?
Magic number. So magic numbers are, we see this a lot mainly within NumPy, or just like long kind of nested list accession. It's at some point, what is the 0th, right, dimension on this array? At some point, we just say 0 so many times that you give this to someone else. You say, oh yeah, just get the 0th dimension. They're saying, they're like, what's the 0th, right? At least James has a nice comment saying height, width, RGB, and time in his code. But we can use something like xArray to actually explicitly label those, and then we can access those underlying dimensions by their names instead of by some arbitrary, as we refer, magic number.
Other comments, other suggestions? Does nobody want to comment on the string manipulation here? But go on.
I'll add
one thing that's a pet peeve of mine is passing open file right into a function, just losing access to the file handle and then being unable to close it. I always prefer to use context managers whenever I'm dealing with any sort of file, just to make sure that they're always closed, because every once in a while I'll run into a weird file type that's something wrong.
Yeah, and to build on that, right, by leaving these unclosed file handlers, we leave some room for them to be either closed improperly or even corruption. And if this is all of our data that we've collected, that is the last thing that I'm sure we want to happen.
One other comment I would have.
First Tom, and then.
Is that we have file 1, file 2. If in the future, again, I don't know what the context of this is, but if you get a 3rd detector or a 4th detector, you'd have to go through and add a whole bunch of lines of code. Adding each of those, it might be better to do this as a file list, which you then iterate over to build an image list, and then work with that list structure all the way through. So as you change the number of elements you're working with, that automatically propagates.
Yeah, I was actually going to add as well to that comment as well, just because I do see as well like a lot of repetition. And if this will be like a code that will be utilized probably once, and we would just like to do something real quick, it will be quite efficient. But if we're meaning to use different type of data sets, for example, like we could have other images that have, for example, like 4 channels, and that will add up. So we'll probably just try to reduce that repetition either by using functions, or as I mentioned, as it was mentioned before as well, like lists or something. Just trying to minimize the amount of times that I'm using or executing the same line several times. So that's just one observation in case that we would like to automate this and accept different type of data sets.
I think also I have a just sort of, I guess, a preference. At the bottom, it's like almost the same exact string being saved to each time. And that gets really hairy to edit because there's a lot of splits and -1s. So I would personally just make a variable for all the file string parsing, and then only change the red and the green and the blue. So that would be the only things that you would edit.
Going back to the dimensions, I would just point out I like to leave comments or put an actual assert statements when there are assumptions that the code is making. So for example, the HWCT are defined as the shape of image 1. And so you may assume that image 1 and image 2 are the same dimensions, or at least image 1 is smaller than image 2 on all of the axes. So you can add an assertion or at least a comment so that in the future when you're coming back to this code, you can understand why it might break for new data.
Going back to the file naming also, I often like to use pathlib or the OS modules to generate my path names because the syntax is usually a lot more concise and easier to read. And OS, of course, has things like os.path.base name, so I can actually get the name of the file instead of having to do these like file.splits. And also, functions like this are operating system agnostic. So if a person's running a script like this on Windows, they're not going to get messed up by the separator being backwards.
These are all fantastic suggestions. I think what I'm going to do while we are hearing our prepared remarks is I'm going to see if I can incorporate as many of these as possible into my code and bring it back to the end. And so with that said, why don't we open it up for maybe one or two final suggestions? Then I think I'll be able to try to incorporate all this feedback, and we'll see if this is actually going to result in better code.
Consider F strings.
Okay. And maybe one more.
I think the biggest computational issue for me is, well, there's two, but I'll say one. The fact that we're using NumPy concatenate to just keep extending the same array. Instead, I would make that into a list and just append to the list. And then when you're all done, if you need it back in a NumPy array, convert that list into a NumPy array. The list appendtions are just going to be much faster because they're a data structure designed to grow and shrink with your data. Whereas a NumPy array is stagnant in the amount of space that it takes. So each time you append to it or concatenate on it, it has to copy all the underlying data, make a new array, and then insert that new data.
Fantastic. Who knew that 25 lines of code could have so many things wrong with it? But with that said, I think we have enough to-dos in here. I'm going to take this back, and I'm going to see if I can make a couple of changes to incorporate this feedback. If we don't have time to see the fixed up code by the end of this session, do know that we will be emailing out both of the code samples, the before and the after, along with all the suggestions, along with the HD video of this session. And so if you have your own suggestions, your own thoughts, please do put them in the QA widget or in the general chat. We'll try and incorporate them, and we will be sending all of these out at the end of this session once everything has been produced. With that said, why don't we move over to our next item for the evening? Would our guest panelists like to share their screen and share with us a couple of prepared remarks to start our discussion? I'll hand it over to them to get started.
So I'm hoping, this is the typical ritual that we do now. Can everyone hear me?
Everything is perfect.
Wonderful. Thank you so much. It's a pleasure to be invited to this event, and I think it's really a way for me to share some of the passions that I have, but also some of the passions, as you already heard, that my team has, and really talk about how software is one of the foundations of science. And I think before we talk about the foundations of science, I think we also want to talk about what are we actually doing, and why does this open source and open science sort of help us? And so my talk is a little bit of a two-parter. It first focuses on what are the questions. I'm an astrophysicist. What are the fundamental questions we have about the universe? And then on the second one is how do we work in new ways together to answer these questions better, faster, and potentially even fairer, including more people from more communities, and being able to really get at the bottom of these questions that many of them have been standing and have been asked for 50 years, 100 years. Anyways, on that note, my talk is exploding stars on your computer, and so I'm gonna first jump in and discuss who I am, because I think that might help you. I'm an assistant professor at Michigan State University, and I'm split. My personality is split into physics and astronomy, which I spend some of my time in, a new center, which is computational mathematics, science and engineering, which really gives split personalities like me, who are interdisciplinary in their nature, a home where we can all work together on open science, open source software, but also on the algorithmic side, where we can bring computational math together and figure out things. And so my research is also split on the astrophysics side. I work on the astrophysics, and part of my time I work on data science, which is a smaller part of my time. And so in the astrophysics, I think about life and deaths of stars, but I also think on the research infrastructure. I'm going to talk a little bit today about this. And so on the lives and deaths of stars, my group is talking about graveyards of stars, and I'm going to introduce a little bit later on exactly what I mean with this. Talking about surviving companion stars that are left over when their companion exploded. We think about stars near the most massive objects in the universe, which are millions of times the mass of the sun, and how they got there and what they tell us about reality. In general, general relativity is something in there which is like, I think, one of the foundations of like, our reality as physicists. I talk a lot about exploding stars. How do stars explode? How can we use AI in physics? As I said, I'm the PI of the simulation code called TARDIS, which is an open science code. And so I also talk about AI research assistants and like literature search tool, but this is something that I'm not going to focus on about in this talk, but I'm happy to answer questions about this. So first of all, let's take a big step back and say, like, what is astronomy? Like, what do we study as astronomers or astrophysicists, which I'm going to use as synonymously in this talk. So the first thing, like, in the smallest scale, what astronomers care about, and like what our ancient ancestors cared about a lot, were like, comets, which you can see, but also specifically planets, things that sort of move in the night sky, and then also, I mean, further along stars. But I mean, the fundamental, like the smallest scale in our science is the entire solar system, asteroids, planets, and our solar system. So if we sort of like take a little bit of a step back, we can think about like, the lives and deaths of stars. This is sort of the next bigger thing in this science of astronomy. And we're thinking about like, where's our sun? Our sun is our closest star, and how does it relate to stars in our galaxy and in our universe? So we take another step back. We can think about like, collections of stars, our galaxy. And I'm hoping that you have the chance in the southern hemisphere, but even in the northern hemisphere, to stand out in an unpolluted night sky, and you can see these wonderful, I think these pictures are really amazing. You can see like, the collection of stars stretching across the night sky, and really learning that we're part of a larger ensemble, which we call the Milky Way. And we've like expanded this and have sort of looked outside, and for 100 years we've known that the Milky Way is one of many collections of stars, which we call galaxies, and like goes further out. And then obviously like one of the biggest things, like, stepping even further back and saying like, how does this all work? How does the entire universe work? How did our universe evolve from in the last 14 billion years? What happened at T0, and like how did it evolve from there now? And it's really, cosmology is really the study of us, the universe, and everything. So, I mean, these are all different zoom-ins of the same topic, and we're working sort of on some of the intersections of these. Mostly what we're doing is, my group is studying the lives and deaths of stars. And so before we go into like, what we specifically study, I also want to quickly say that there's two phases of science, and essentially we're a bridge between them. One of them is like the experimental side. We go out, we make experiments. If you have kids at home, I'm sure they make many experiments, but ultimately, like, this is a way for us to like understand reality in its rawest forms. But on the other hand, we want to know what rules govern this reality. We want to know, like, can we predict reality? I mean, predicting the future has been like, a human goal for a long time. And so we've now come up with a framework, which is mathematics, to sort of make predictions. And so a goal of scientists is finding the synergy between theory and observations, and figuring out what are the fundamental rules that govern our reality and our universe. And so my group is trying to sort of like do a bridge. And so, as I said, we study lives and deaths of stars. And so, like, to give you a quick overview, stars are born from giant gas clouds. I mean, it's gigantic gas clouds that collapse and form really hot parcels of gas in their center. And essentially, like, stars are born and planets are born. And then they live for millions to billions of years. And then at some stage they die. And some of these deaths are very violent, and they explode, and they can outshine all of the light of their galaxy. For example, on the lower left-hand side, the bright picture, the bright little dot, that is a single star outshining billions of stars around. So, I mean, these things are happening. These things are very exciting because they make heavy elements like silicon, which is the computer that I'm sitting in front, and iron, which we need to survive, to bring the oxygen to our cells. And essentially, like, the questions that my group is focusing on is like, on the stellar side, how do they live? Are they alone, or do they live alone, or are binary stars, are they together? Do they go out quietly, or do they die in a flash? As I said, like supernovae go out in a flash. If they go out in a flash, what makes them explode? Do we understand these explosions that are billions of times brighter than the sun? Can we learn something about the fundamental rules that govern the universe? What does their dying light tell us? This is a specific focus of our group. And what elements do they really? Like all the elements, like gold and iron that we have in the universe, do come from exploding stars. They're not there at the beginning of the universe. So as I said, like there's theory and there's experiments, but there's a bridge, and that's computing. So we can encode the fundamental laws that we think we found into computers and say, like, what if? Like, we can make what if machines and say, like, if we encode this and we can run this. And the cool thing with computers, you can speed things up, right? You can play YouTube at 2 times the speed or half the speed. And so we can really study these things up close that we normally just see very, very far away. And so I think this is a very nice simulation. This is, I think, from one of the labs about a star that is around roughly the size of our solar system, shrinking to a star that will be the size of New York City, but weighs as much as the sun. That works. And you can sort of see, like how you have a blowout, and essentially you have a collapse in the middle. And I think it's a really nice thing just to watch and take this in. And this is millions of hours on CPUs on several of the high performance computing facilities. And so I've talked a little bit about this is the experiment that this is the theory that we talked about. But on the other side, I'm gonna move on and move to the next video. What is about the actual experiment? The experiment has been set up for us, and then essentially that works. The experiment has been set up for us, and what we as astronomers do, we build devices to observe. And I think one of the coolest experiments that is coming up is the Vera Rubin Observatory, and with it, the Legacy Survey of Space and Time. And for this, I'd like to also play a video, and I asked the organizers to cue the video.
The night sky, our window to the universe beyond. Immense, mysterious, powerful, quietly beautiful. Cosmic events at the edge of our imagination unfold in the darkness, ready to be discovered. When we look at the night sky, we see into the past. Untold stories carried through space by light, the great historian of the cosmos. Technology has evolved over centuries, allowing us to look farther, to the edge of our horizon. We invented telescopes to explore and cameras to capture these traveling messages. Yet the changing cosmos remains unseen. A new telescope opens its eye and captures it all, the objects that move and those that flash, even those we cannot see with our eyes. Every few nights, it covers the sky, finding all that has changed. And within minutes, new glimmers of activity are carried around the Earth to anyone waiting to explore them. What will you discover that no one has seen before? It's time to find out.
I mean, this video always, it gives me goosebumps. I think it's such an amazing video, and I'll actually continue sharing my. Oh. I think this is an amazing video, and all of the story that's behind this. This is not a science fiction movie. They're telling the truth. There is essentially this new observatory coming online, which will bring like petabytes and petabytes of data. And so I think this is a story from on the experiment side, that has been happening over thousands of years. For example, the sky disk of Nebra is thousands of years old and was one of the first images of the night sky, so to speak. They recorded this. And like Hipparchus, a couple of thousand years later, was 400 stars. And so the SAO catalog was 300 stars in the 1960s. And the Gaia satellite, which was released very recently, has brought 2 billion stars, measurements of 2 billion stars. And I think the Vera Rubin Observatory is a natural evolution. And so there will be 37 billion objects over 10 years, 5.5 million images over 10 years, and 60 petabytes over 10 years. And so I think this is really what my group is about, bringing the simulations that I sort of showed together with these new telescopes and with the new data that is coming online. And we are really thinking about how do we analyze this data with complex simulations, which has been for now beyond human capability. And so we need to think about how AI and machine learning and computers and specifically software can help us with this. So one of the ways that we think about solving this conundrum is that the way that academia has done work is a way of few tens of people. It was conceived in a world where very few people had the chance to go to school or university. It is hundreds or thousands of years old, and potentially, and this is our belief, is outdated and will not allow us to understand these or answer the questions that we are trying to answer as humans in the future. So we really have to rethink, and this is now the second part, of how we work together. What are the important trades? What are the important skill sets? And what are the important things in our communities that we need to sort of think about? And so open science is one way to sort of think about this. And I'm going to talk a little bit about the TARDIS community, which is a NUM-focused, fiscally sponsored project. And it's an open science community, it has been for a while, roughly 10 years old, and has grown. And so this is one of the things that I think would be really interesting to also discuss, how do other people do open science. So, this is only part of the team. I will show a small fraction of the team. There's many more involved, and I'm apologize to those that are involved. At Michigan State University, some of my grad students you talked to, Jack O'Brien and Sona is there, and Andrew is there, and Mark Williamson, who is at NYU, is also sitting with me. He's also in the room, and so these are the astrophysicists. But we don't believe that these questions that we have about the universe and tackling this data that comes from the Vera Rubin Observatory are solvable and are tackled if we don't include people that have different points of view. So one of the things, our team is built around interdisciplinarity. We have computer scientists like CEO and Stuart Archibald that are really thinking about how can we make it easy for people to write code that is very fast on computers? How can we take this away? We have Jalaj who says this is nice that you write code, but how do you make sure that us humans can understand what this code does and understand what the simulations do tell us? We have Alice, who was helping us with software architecture, Athava, who's working with us on restructuring the code, and Jenny is also one of the visualization people. And we also have unfortunately for now, our lonely astrostatisticians who says data and simulation, the way to compare them is by statistics. And so I'm going to first talk a little bit about the inside of the collaboration. I'm going to briefly sort of highlight what it is. And so essentially the way that our collaboration thinks is there's a scientific question at the center. The center is the scientific question. And we're trying to figure out questions as I said, how old is the universe? Where does gold come from? What is gravity? How long do stars live? How large is the universe? What forces govern the universe? How special is life? And is the universe forever? And so going from the center, we are building our collaboration around. So we have our computer scientists, as I showed, our statisticians, people that are experts in experimental data or observational data, and people that are experts in simulations. And so really, all of these people know the scientific question. It is not that the simulation people sort of go and tell the experimentalist, like, this is what you need to do, or that the experimentalist, like, do this. But everyone has some training in computer science, has some training in physics, has some training in statistics. And so the fundamental theme of our collaboration is we're not here to know, but here to learn. We learn from each other. And it's truly important that we actually all understand what we're here to do. That there's no like gatekeeping, or that there's no like, oh yeah, I mean, this is too hard for you. But that we truly can work together. We're educating each other. And so this is, I mean, our collaboration is obviously like, there's an inside, but we want to make sure with this open science nature that we also reach the outside. It is not only like, us, but we're embedded in a community. And so essentially, like, as I said, at the bottom is a scientific question, and like, there's a collaboration around these different scientific questions that does this. But we collaborate with the wider community through GitHub, which is, we feel, is a central place for collaboration. There's other tools, but I think this is one that I would like to mention. And so, like, essentially what you can think about is like people come to us and say like, oh, I'd like to have this question. And then the whole collaboration like thinks about this. And there's a couple of things that we sort of have learned to do and we think like really are helpful is like simulation. Our simulation code is open source. It's on GitHub available. There's no closed version or anything like this. Our data is open. Many ongoing discussions about the physics and the code are in the open. Like you can go to GitHub and you can look at them. And so we have, I mean, as I said before, like the true important thing is like, training and asking question and curiosity are at the center of this new style of collaboration. And we have an openness to interdisciplinary knowledge. And so our goal is to learn, and ultimately our goal is to learn the unanswered human questions. It is not only to learn from each other, but I mean, then in the end, we learn how old is the universe? How long do stars live? We place a strong importance on mentorship and training. We have transparency on all levels. And so with this openness, we also have an openness to changing the way we do science. And I think this is like the second part of my talk. This is also a discussion I'd like to have. And we believe that this is a great formula, and we're very lucky. It's a formula for strong engagement, and we believe this is the way forward. So a couple of things that I want to mention is like there's always summer project with my group. So if any undergraduate students visiting or graduate students is listening, or someone who's new to open source software, we are available at TARDIS.sn/TARDIS. You can follow us on Twitter. You don't need to be an expert coder, just interested in working in a team and learning. Most of our participation is remotely. I mean, obviously, sometimes it's very nice to sit in person and like have a coffee together, but most of this is remotely. Skills building and mentoring, as I mentioned, is fundamental to the way we do science. We are participating as a mentoring organization in Google Summer of Code. For this year, it's too late to apply. The applications have closed, but it's good to know for next year. And you can either contact me or team through this email address or reach out on us on GitHub. And so this is where I want to stop and like thank the organizers for inviting me and thank the audience for listening to this. But before we sort of like go on, I thought like what are things that might be interesting to discuss that we can discuss and like some potential questions. Like one of the things is how does the DOE community collaborate? I think this is mostly focused on the DOE community, but this is any scientific community. What are the struggles for interdisciplinarity that we faced some, and we would love to know what you faced and what you did to overcome them. How do you collaborate on science? How do you collaborate on software? And how do you collaborate on data? Are there specific formats or ways to do this? How can we improve as science to make it easier and quicker for us to get results out and to also build more sustainable, equitable, and inclusive communities? And so I really now want to go back, and these have been our ideas, but I would love to hear what you think. Thank you very much.
Thank you for that. I'd like to now open us up for some general discussion. So for our panelists, were there any general comments you wanted to share, or should we dig right into the questions that were posed to us by our guest panelists this evening? There was one question from the Q&A that I'll start us off with, and the question was about this term open source, because I think we see in a lot of scientific research, open source can sometimes mean I put the paper out there and I also just put whatever the state of my repo for the paper was on GitHub. And it can also mean like a large project, I put it out there, I'm watching it for pull requests, I have issues, I have a contribution guide. And if the latter, isn't that an enormous amount of effort that you're basically adding to all of the things that you have to do to get a publication, to get submissions going, things like that?
I mean, maybe I'm happy to start off on this question. I mean, you're absolutely right. Like taking source code, taking a Fortran 77 source code and putting on your website is open source. And I also want to make sure that, like, you know, we as the sort of new vanguard of openness and open science, like we sometimes are very critical of these people that sort of did this. But I mean, one has to argue that at least they did this. At least they put it out there. And like when GitHub didn't exist, like, you know, when they were like, you know, maybe assistant professors or postdoc, they at least, like, you know, took the time to put their code up there and say, like, anyone can look at the code and can play with the code. But I think, like, you know, we've evolved, and I think, like, you know, the new way sort of, like, you know, I think to share code is in an open collaboration style. So open source is like one important aspect of open science. But it's not enough. I mean, you know, if you really want to have open science, you need to be able to engage with your community, and you need to think about, like, you know, not only how to make, like, you know, things accessible in, like, you know, a technical sense, but I feel like also how to make things accessible from a societal point of view. How do you make sure that, like, you know, people can use the code and, like, you know, are trained how to use the code and things like this. So I think like open source in its nature is not enough. And I mean, people will argue and will say, well, I mean, no, that's right. Oh, you're right, Wolfgang. But I mean, the funding's lacking, and this is, yeah, I agree with this. NSF has never supported NumPy, for example, which is, I think, a big shame. Or Matplotlib. I don't know if Thomas can argue in this. And I think academia is really lagging behind of what it means to be a scientist in the 21st century. And I think we need to think about this very carefully, and we need to think about, like, how do we make sure that we keep up not only innovating in our individual domains, but also innovating as the sort of field of science.
I'm actually very curious to hear from the folks who are closest to the science, Andy and Tanny. Is it enough? Is it better than nothing if somebody puts out a paper and you're reading it and there's some code somewhere, but it's not really documented, it's just dumped on a website somewhere on GitHub somewhere? Is that better than nothing? Or is it something that you can work with? Is it a starting point? What is your experience with this very shallow view of open source?
I think from my perspective, something is always better than nothing. At least you have a way to, like, test your own code to see if you can reproduce the results. It may take more time to figure out what other people are doing, but I think if you practice at it, you'll become more literate, and, you know, maybe you'll understand whether or not it's a good investment of your time to look through the code, or if it's not a good investment. But it takes maybe a little bit of time to figure out what is code that's worth the time investment. I'd say that's the hard part about it.
Yeah, I think that adding to that as well, I wouldn't necessarily expect, like, a scientist trying to, for example, keep different versions of the same code. Maybe someone was just working on something once, you know, froze that version, posted it just to share with everybody else. And I mean, I agree with Andy that that's better than nothing. That's a starting point. But I think beyond that, maybe just having, like, a really basic guideline on, you know, what is necessary for everybody else to use it. For example, like, trivial things that maybe do come to mind, like, what are the requirements? Do we have a list of requirements? Because I have seen repos that probably don't even have that. And then I think at the minimum, probably a brief description of the data, even if they cannot probably share the data itself, probably just a brief description so that at least at the very minimum, I can take a very similar data set that the one that they were utilizing and just feed it and run the code just to make sure that I can kind of like just run it at least once. I think those very minimum things that at least at this point come to mind, and probably the rest of the panelists may have different ideas regarding these minimum qualifications. That will be like a great start, and I think that probably that will make different repos or different source code actually accessible and open source to other scientists.
I may follow up on this. I very much agree with both Tani and Andy, and I think this is something that, like us as the open science community, often a little bit bad at, and we're a little bit exclusionary. We sort of like, if someone shares a code, sometimes we go and say, well, it's not on GitHub, it's not version controlled, like, what are you doing? But what we should be instead doing is we should say, like, hey, you tried to share your code. This is great, and this is wonderful. This is the first step. How can we help you to, like, go and share it in a way that is more accessible to people? And I think this is something that we as the open science community need to like take on more, and not be like, because I think there's many people that like to share and that want to share, but they don't know, and they're afraid that someone will judge them and say like, oh, you did it wrong. And I think we need to lower this barrier to entry. And obviously we need to help those people versus the people that say like, I'm unwilling to share. I don't want anyone to see my results, which I think fundamentally is unscientific.
And this
something that I'm hearing is that there are so many different ways that we might mean share that it's helpful to carve up the different meanings. And there's a blog post that describes this really well that I'll just quick. There's publicly visible source code, which we covered. There's publicly visible with a license for reuse, so people know that they can use it. That's a really important step to take. I would argue you should always at least get to that second step if you're going to put it online. Then there's accepting contributions. So now you have other people's opinions in the mix. Then there's open development, where you try to have a lot of the communication and the planning in the open and not just the code. Open decision making, where everything is the communication is fully public, it's similar to the last one. And then stepping all the way to multi-institutional engagement, where the institution that created the code now has to accept possible community-driven directions that they don't necessarily agree with or prioritize. And if somebody means one of those levels, but you hear a different level, there can be a lot of fear, uncertainty, and doubt. I'll post a link to the blog post by Matt Rockland that I quoted from in the event chat.
I saw Thomas also went off mute. Did you have something to add as well?
I was going to say there's a quote that I've heard from Lorena Barbara, but I forget where the source of it is, that the paper is not the academic product, it's the advertisement of the academic product. And the underlying source, if you're doing it in your computational main, is the actual science that you've done. And if you only put the paper out, you're only putting a billboard up saying, I've done this, but you haven't actually shared the science that you have done.
So Tom, from that perspective, if you were a scientist putting out a research paper, working even up to the deadline, does that change the allocation of effort or how you break down your time in terms of making sure the code is available, making sure the data is available, it's documented even to the degree that Tani suggested, and working on the submission itself?
Yes, I think you should start from the beginning with the mindset that any code you write is going to be shared. Because again, just writing the paper saying we've done some computation, you can also write that paper without doing the computation. And just assuming that your full work product is going to go out is probably where I would suggest starting from.
And maybe keeping in mind that your most frequent collaborator is your future self, that this isn't necessarily for an abstract someone else who won't care, but really for you in 2 years. Yeah.
I wanted to add, I really like Thomas's point about the paper being the advertisement and not the final product. And I think it's on all of us who are interested in open science and are also connected with academia to really explicitly value not just the advertisement, but the final product, because there are many people, I myself am a graduate student who has contributed some code
that is open source in a way that's not fully developed in an open source manner is a huge time commitment to do that sort of thing. And currently, we still face this problem where most people in academia only value the advertisement and the citations to the papers, and things like GitHub metrics for how many times your code has been forked, or how many times it's been cloned, and how often it's actually being used to do science, are not actually counted as a valid way of measuring your contribution.
How do you justify that additional time commitment then? Because you're talking about graduate students like yourself who are already overwhelmed with other things that other responsibilities, other things they have to do, and now you're asking them to do even more.
I was going to mention, I think there's just no true incentive system set up for this yet. There is an incentive system for publish or perish, right? That's your career. But there's no incentive system to, generate anything that's going to be forever standing in terms of a code product, right? Because you can get published and have a high impact factor with or without contributing to open source or open sourcing your own code or your own work.
So in my experience, I find being part of a large collaboration helps a lot with giving me the motivation to actually contribute code. When I write code to try to do something scientific, it's, as a member of the collaboration, I'm already familiar with the code base. It doesn't take that many more keystrokes for me to do a git commit and git push, and then have these extra things up on the repository. Also, through programs like Google Summer of Code, we do have funding to hire people like undergraduates at other universities to take care of some of these things for us. For example, TARDIS has extensive documentation that outlines all of the physics that we run through in a very educational way, and much of this is written by these students that are extremely time-intensive projects that we don't necessarily have time to do ourselves. But because there are these bigger organizations that can fund us to have these people, it really takes a lot of the work off of us when we're trying to get science done.
I'm curious about Cameron's comment about incentive systems, because the incentive system isn't just do you keep your job or not, it's also do you get the best graduate students? For those of you who are postdocs or graduate students, is it an incentive to join a lab where that lab is known to have open collaboration, open code, and this kind of focus? Is this something that attracts the best quality students?
From a postdoc.
First Tanny, and then our folks in New York.
Sure. So I was going to say, from a postdoc perspective, I think it is quite important, because when I was job hunting right after I graduated, I was looking for something a little bit more open source, mainly because I truly believe that we should work more towards having open source as the general kind of like rule. Is one of the reasons as well why I went into this career. But ultimately, because during my graduate studies as well, many of the things that I was working on were private. That was a completely different project. It was justified for the things to be private overall. And I always kind of wanted to contribute a little bit more with respect to these things. So I think that for that reason, it was very important to me. At the same time, when I was job hunting, I did also notice, and I think this is also kind of like that, that idea, like that. Whenever we're job hunting, kind of having this GitHub presence is quite important. And I know this is more related kind of like to this job situation. But at the same time, I think that as a scientist too, it does say a lot when we have quite a GitHub presence, and when all these things are open source. These are not just contributions that are in private repos. If they are open source and everybody can see them, I think that that actually means that we are contributing to science. And I think it makes a big impact, not only from kind of like that job perspective, but for our career, for our development as a scientist. I think it's quite important. So it was quite a very important part when I was selecting, in this case, where I was going to do my postdoc at.
Before we hear from our guest panelists, there's one clarification I'm curious about, Tanny. You said having a GitHub presence is very important. Is a GitHub presence very important for the postdoc, for them to find their next job and to be evaluated on that? Or is it important for the lab or the job that you're joining to have to show that they're supportive of this?
I think it goes probably both ways. I mean, of course, for the postdoc perspective, once they will be contributing to the next step of their careers, it will be a very important aspect to have a lot of contributions to these repos. But also, I mean, this is particularly an aspect too of our job. Like whenever we will be reporting back about our funding, about what are our contributions in this case to where all this funding came from or went through. This would be basically our list of evidences, because but yeah, it means a lot, I think, for both parts. And at the end of the day, I mean, this is just so that we can contribute this with the scientific community. So I think everybody at the end gets benefit in many different ways. Ultimately, people may have a different perspective on how they look at this, but I think everybody wins in this situation. So it's a good.
And our colleagues in New York had a follow-up?
I mean, I think one of the things that the harsh truth of all of this is we will be judged by the scientific output. And so, like, I think, like, that's why I mean, the TARDIS collaboration is not only thinking about, like, open source and open sort of like collaboration for our software, but that's why we're thinking, like, the way for us to be successful is, like, to change the complete paradigm of, like, working together and then being able to put out more high impact and better papers. Obviously, this is hard because we're not only, like, working on the science with the given method, but we're developing the way or the collaboration method on the way of doing science. But I think ultimately, like, the way that companies went, and I think Google, and I hate to call it a name, but Google is a really nice example. Like, when Google was founded, the job offers they had significantly less money than other people, than other companies, but they were a nicer place to work at, and that's why people worked at them. And so I think, like, doing both of these things, changing the way that we collaborate and changing the way we make academia sort of, or this open science collaboration look, at the same time, like, switching to an open source model, I think that is hopefully, well, that is what I'm banking on. This is what I'm trying to be trying to successful.
I think we've chased that thread adequately. I want to open up for any other general questions. Otherwise, I have a question for our guest panelists. For our guest panelists, TARDIS, the major project that you contribute to, is now a couple of years in, almost, I think, 10 years in, with almost 100 contributors and thousands of commits on GitHub, thousands of lines of code. What was the biggest surprise from managing such a large project that you never anticipated before you embarked on this?
So one of the things one of the biggest surprises was, like, when we wrote TARDIS, and I think the first commit was done in December 2011. There was no, and until this day, I think there is no real open collaboration code out there. I think that for the capability of TARDIS, there's nothing out there that sort of did the same thing at the time. And so for the first, I mean, as I'm preaching open science and open source, I should be honest, I think for the first, 2 years or so, I did development. It was mostly me. I was a postdoc at the time, and the co-founders, Stuart Sim, who sort of, like, had written codes like this before, and sort of he sort of helped me with the physics. But I mean, I wrote most of the code, the initial code, myself, and I was afraid that as soon as I opened up, people would take the code and scoop me and put out all these amazing scientific results. And, like, I had no chance of, like, catching up, and I would be, like, I would be lost, and, like, people would make money on my work. It was very surprising to me that this is not the case. Like, for other people to use your code, you need to make the barrier of entry very, very small. And so, like, I think it's sort of rare. I think, like, once you reach NumPy or these kind of stages, like, it sort of is a snowball effect. Like, as soon as more people start to use a code, it's a snowball effect. But getting this initial barrier of entry down, I had thought, like, people would just take the code and do something with this. But I had to go to conference and say, like, hey, this is a thing. Do you want to try it out, and sort of get people excited? I mean, once the ball was rolling, it's rolling, and, like, we have many citations. But I think that was one of the sort of, like, difficult hurdles of all of this. Also, working together with people from different disciplines and like learning their individual peculiarities. There are many things along the way, but I think there was nothing really that like, no, there were many peculiarities, but nothing that sort of, I wouldn't say, stood out. But I don't know if, like, Mark or Jack, who are now, like, part of the core team of the collaboration, and are also, like, having a leading role, I don't know if you guys have found things that were surprising to you when managing.
In relation to what you said about the fear of someone taking your code and just running with it, I feel like, if anything, TARDIS being open has encouraged more people in the scientific community to come to us with questions, asking help. We get on their papers and they make contributions back to TARDIS. It's like basically the opposite of everything that people fear with this.
Yeah. I guess just to add to that a bit, so Dan and I met in grad school when I had put up some code on GitHub that was solving one part of a standard problem in optical microscopy, and he had written the other part of it. There was MATLAB code and IDL code floating around that solved both, and I got this email saying, "You have half of the code, I have half the code. Let's be friends." And that's now in a project called TrackPy. It's probably being used by like 100 so labs for working with light microscopes, and eventually Dan ended up working with me at Brookhaven, and that's been an extremely productive professional relationship. So you make friends.
Now, I want to open it back up to some of the questions that were raised in our guest panelist presentations. Specifically, how does the DOE community collaborate, and what are the struggles for interdisciplinarity? Do any of our host panelists want to speak to this? I will say, on my own side, as external to DOE, my view seems to be that there are pockets within DOE where there is very high levels of collaboration, and then complete inability for two areas where they do largely the same thing, but they're not quite aligned to talk to each other. So for example, it seems like labs like, or sites like APS and NSLS2 collaborate very, very strongly, but then some other sites like Livermore don't collaborate as strongly with APS or
I would say that just like in academia, the collaborations are very application specific. So it's, both NSLS2 and APS are small parts of a much larger lab that we're within. And while the facilities have very good collaboration, that's because we both are synchrotron facilities that have very similar user bases, because our users go to both and are solving very similar support and science problems. Whereas someone who's like, we have a much better collaboration with APS than we do with Rick on the same site, because they're just doing very different science and have very different needs. So I think you have to start with the people that are closest to you and then build out.
But is the lack of collaboration there appropriate? Because clearly tools like those in the Blue Sky stack are very general, tools like tiled. Does it really matter what the specific application is? Or is it really the technology is broadly applicable to many, many use cases?
I think there are, I very biasedly think the technology is applicable to a broad swath of problems. However, within domains, people have, these are not like, these problems are very universal problems, and that's why I think these tools are general. But it also means that within domains, groups of people have solved those problems for themselves in a way that works, that may be very domain specific and may not transfer. And so the threshold of replacing the thing you have that's very tuned to your problem in your domain, that bakes in the assumption that you have samples of such and such type, or baking in the assumption that you only have one detector that is a streaming detector for the collider experiments, the general tool is going to be harder to use out of the box. And it's not until that you've built up a very, very large other user base and fully, validated you actually are fully general, that it's worth going and replacing someone else's tools with something new.
I'm curious to hear from Andy. Does this track with your experience as well, that the lack of interdisciplinary collaboration does have some reasoning behind it?
Yeah, I think so. And I think part of it too, I agree with what a lot of Tom said. I think that's the experimentalist problem, especially if you have experimentalists writing code. They have maybe the same philosophy. If your instrument is working, why are you going to take it apart to make it like 5% better, that just doesn't make a lot of sense because you risk breaking it. And I think the other aspect is, sometimes the lab is working on things that maybe they can't share, and so it's sometimes difficult to understand what you can and can't like widely collaborate on.
I mean, if I may jump in there and talking specifically about interdisciplinarity and I'm known for having strong opinions. Probably most of these strong opinions are wrong, but anyways, so I think one of the true problems in academia is the root of many problems is that we have departments. We have department of chemistry, we have department of physics, we have department. I mean, I think this is fundamentally something that is wrong with universities and academia. Currently, I'm looking at my phone here, Google and Apple and things like this, they build a company that makes phones. I mean, they make much more than this. They don't only make phones, but I mean, let's say they make phones and they bring together people from have humanity backgrounds, people that have an engineering background, people that have a physics background to solve one question. And so in science, we don't do this. For me, this is crazy. Why don't we find the big questions and then assemble teams? And once these teams are done, we find the next questions. And then people that worked on the supernova question will go over to the genomics and bring ideas over, right? I mean, people from Facebook go to Google and bring ideas from Facebook, Google, or any of these other, I'm just mentioning companies. But it's nuts that in 2022, we work like we worked 400 years ago. And I think this is one of the departments are the root of many of the evils in academia. I think this non-collaboration and I think many of the exclusionary stuff comes from the fact of this is one little camp that you're sitting in, and you can either come in or not come in, but I mean we make the rules rather than saying we want to solve this question. And end of rant.
It's a very revolutionary idea. Do any of our host panelists want to comment on this?
I would say that I think it's a really interesting approach, and I think the early adopters of that approach could stand to benefit a lot. I think it's just something that's going to take time to grow as a way to collaborate and answer these kinds of questions. But I think also it's using things like GitHub and the internet and even the SciPy community at large. There's lots of ways to learn about different kinds of software projects that maybe instead of you writing your own little tiny piece of code to do your one tiny thing, well, maybe somebody's written 90% of that already, and it's worth the time to go and look through their documentation. So I think in terms of trying to make, large collaborations to answer, similar questions, having documented code and things like that are really important if this is something that you want to champion. But, it's clear that you're doing that, so that's great.
And Tom?
I'm also known for having lots of strong opinions. I'm going to push back that not all interesting science are these big questions that need a giant collaboration to answer. I think there's still significant space for, small group, lab bench scale, particularly experimental science, which my training is as a small scale lab experimental physicist. I think there's a tremendous amount of little things you can still go after that have tremendous, can have high impact and value, that those groups don't need to be one monolithic, one massive collaboration, but they need access to lots of little tools from lots of different people. And so while the openness is still there and still critical, it's not in the same organized sense.
I apologize. I mean, what I meant was when I said answer questions. I fully agree. Not everything has to be on an LHC scale, but even for these small labs, even for very small, for detailed questions, I think it would really help to bring in you have a team and that consists that have different expertise, and you hire a small 5 people for one question that you sort of have. I don't mean to say we can only have 300 or 3,000 people on a collaboration, but even a team of 5, there should be a visualization person, there should be a software person, there should be a physicist, and there should be a biologist. Maybe it depends on the question, obviously. But I do mean to say I think interdisciplinary is fundamentally something that is not valued in or not foreseen in academia, but it's I think crucial for making progress.
Other thoughts, other comments on this very large question opened by our guest panelists? If not, I'd like to take us out with the final question. The prepared comments from our guest panelists were really focused on how do we improve collaboration? What are the major pain points? What are the things that make this unnecessarily difficult? Things which could actually be addressed in the small scale by participants of this call itself. And I'm very curious to hear from our host panelists if they have any thoughts of things which are just unnecessarily difficult or stand in the way of collaboration, which is right there in front of you, could be easy if not for something or other.
I can probably add something on that regard. I have been actually I consider myself lucky because I think that overall through my short career so far, I have been very involved in very large community collaborations. And I think one of the things that I have noticed is probably, and what comes to mind first is communication. It's just to effectively communicate among different members that have very different backgrounds. How to just, and that's something that I myself had to learn as well and practice quite a lot. Just, how can I convey a message to someone else that has a completely different line of expertise? Like I will not be talking, for example, like Python and code, how to translate these things so that the message will be exactly what I'm trying to convey, but it will still be effectively delivered. So that's something probably that comes to mind, just to how to be an effective communicator when we are collaborating at a larger scale.
I would say just to further that, I think that's one reason why these interdisciplinary teams are really important in moving forward and answering science questions that maybe are very narrow in scope even, because then everybody can have their own expertise and we can start to reach out. So it's not just having somebody responsible for the visualization and all the different parts of the code, but even just really different people with very different areas of expertise trying to figure out how they overlap and being willing to go outside your area of expertise and learn a little bit of Python, or learn a little bit about an X-ray scattering technique, or learn a little bit about how to do some simulations on a supercomputer. Because if you're willing to stretch a little bit, then everybody else is willing to stretch too.
Dan, would you like to comment on this final question?
We've lost Dan.
If not, Tom, would you like to share with us any thoughts on simple things that we could address to improve collaboration?
So something that I try very hard for in the open source communities I'm involved in is to make sure that new contributors feel safe and welcomed. So I feel what I suspect is one of the biggest barriers to new people contributing to established projects is that fear of I'm going to put up some code and then I'm going to be told I'm a bad person because this code is bad. And just making, I remember my first pull request literally changed a 5 to a 7 and took me about 6 hours to work up the nerve to hit open PR on. So making sure as many people as possible feel that they can open that pull request, and then we can work with them to, if there's things that need to be improved, we can work with them on that, but that they feel safe to do that. And I think just once that first one is the hardest one, and then it gets easier from there.
Yeah, thank you so much for that, Tom. I really appreciate that effort because I too, a few years ago, had that same feeling when I opened my first pull request to a major open source project. And I just remember an hour later, I hadn't heard back. And I was like, oh, I did something wrong. I must have messed up something. And they're just gonna be like, this is wrong. We can't accept this. But I had someone like you who was just like, hey, you just make this little change and then we'll be good to accept it. And I was like, oh. And that definitely kept me contributing in the future.
Andy, and then our guest panelists.
Yeah, I know I already spoke a little bit, but I just really wanted to highlight actually some of Tom's work on scikit-beam. I think it was him that wrote all of this really detailed GitHub information about when you should create like different more remotes instead of just using the origin remote and different feature branches. That was really useful for me because it was written sort of in plain English instead of trying to understand GitHub's documentation. They have a wonderful service and I love GitHub, but I found it not very approachable for someone that was just starting out. So I think publicizing tools like that is also really important because not everybody has the benefit of being a summer student to learn from a PI directly or a graduate student. So.
And our guest panelists, if you'd like to comment on this final question.
I think this is a very important question, and like, I think I don't have anything really new to add, but to sort of synthesize, I think like fostering specifically in the sciences a community that thinks about, that is driven by individual curiosity, and where we sort of go and where we say, well, I mean, we're really here to learn, and not only the new person is here to learn, but even like, me as a senior person, like, sitting down and someone just came out of undergrad and like learned something in physics that I'm sure I've learned like 20 years ago, but never understood. And really like, sitting there and saying like, hey, this is interesting. Like, let's talk about this. Let's learn from each other. I think that really helps. And that really makes it so we're like, I think we're at the best when we are driven by our own curiosity, and like, if the community is driven by the curiosity, and then we can really succeed and can say like, oh, I don't know this, and that's okay. Like no one minds that you don't know. And I think like removing any language where we say like, oh, you should know this, I think that's really on us to make a community that is very very good to sort of like share and work together. And then I think like the open science community, what Thomas was saying, what Annie was saying, is like, I think is really pushing this and trying to make it really feel nice, at least in the last few years. For new people to come and contribute and learn, and like they learn something and then they contribute back. So I think it's a win-win for all.
Any final comments from any of our panelists? If not, as promised, I did actually manage to incorporate all of the suggestions. Behind me, you'll see my screen. I'll hide in the corner here. This is the final version of the code with the suggestions provided to us. I don't think we have time to go over it together, but we will be sharing this along with the HD video of this call. We'll also put it on the Meetup webpage so that you can comment and tell us if there's anything about this code that you think maybe we didn't need to make that change, or maybe we need to go even further, because the purpose of this call is to help you improve the use of scientific computing at your site, whether that be in Python using tools like NumPy, Matplotlib, Xarray, whatever the case may be. Our goal is to improve the use of open source scientific computing within the entire national lab system. And with that said, I'd like to thank all of our panelists for joining us tonight. We will adjourn at this point and resume next month. We'll let you know shortly who our next batch of guest panelists will be. And next month, we will also have another one of these hands-on technical challenges so that we can together improve our use of Python, our use of open source scientific computing tools, and see all of these thrive within our working environments. Thank you all for joining us tonight. Special thanks to our guest panelists. I'm James Powell, and this has been the Python Exchange. Thanks, everybody.